in the field. Allow me to briefly introduce our speakers. We have 5 speakers. The first speaker is Dr. Howie Chen from the United Nations Statistics Division, USA. The second speaker is Dr. David Newhouse from the World Bank, USA. The third speaker is Dr. Joshua Murphy from KGI School of Public Policy and Management, South Korea. The fourth speaker is Dr. Pata Lahiri from the University of Maryland College Park, USA. And the last speaker is Mr. Abhej Komua from the World Food Program, Sri Lanka. Before we begin, I'd like to take a moment to introduce two distinguished leaders who are instrumental in the success of this event. We sincerely thank them for their dedication and commitment. First, we are honored to have Professor Pata Lahiri, the Director of the Joint Program in Survey Methodology, University of Maryland College Park, with us today. And next, we are pleased to have Associate Professor Atipat Thamlong-Thanalak, the head of the Department of Mathematics and Computer Science, Faculty of Science, Chulalongkorn University, Thailand, joining us today. We deeply appreciate their leadership and support in making this event possible. And I now invite Professor Pata Lahiri to share our viewers with us.
I'm Partha Lahiri. I'm the Director of Joint Program in Survey Methodology. I hold a position in Department of Mathematics at University of Maryland College Park. Let me give you a very brief introduction of JPSM. Joint Program in Survey Methodology, we call JPSM, started back in 1993. So we just celebrated 30 years of JPSM last fall. We offer various kinds of program. First of all, we have JPSM on-site program that we collaborate with University of Michigan and Ann Arbor. And we have also partner with STAT located in Maryland. So you offer both master's degree and PhD degree in what we call survey and data science. I have given the QR code. If you are interested to learn more about all our program, you can just go there to our website and learn more about it. We also have online programs. We offer a wide range of courses of various types. It can be 1 credit hour, 2 credit hour, 3 credit hours offered throughout the academic year. We also have short course program that we run throughout the year. Typically, it's covered in 2 or 3 days. And here also we have a wide variety of courses. So if you want to know more about any of this program, you can simply go to the website. You can scan the QR code and you can learn more about it. So I think I should be brief here and I would hand over to the next speaker.
Okay, thank you, Professor Pata Lahiri, for the introduction for JPSM. And we are now welcome Associate Professor Atipat Thamlong-Thanalak to share a few words with us.
Hi. Okay, so first I would like to thank every participant for participating in this event today. So let me give a few words about our Department of Mathematics and Computer Science in Faculty of Science, Chulalongkorn University. Our department is established in 1933, which this year will be our 92 years of our department. Okay. And we have over like 58 academic staff and more than like 600 students right now. We have 8 programs in like both mathematics and computer science. We have like bachelor in math and bachelor in computer science. And we have like master and PhD in math, applied math, and computational science, and computer science, and information technologies. And here are some of our staff that helping running this department. We also encourage our students to have extra curriculum experiences. Okay, not just for academics aspect. Okay, we also help have a special program in math consult to encourage like the study in math for every for new generations, and also have extra curriculum courses for to upskill other parties are like other people as well. Okay. And we also encourage our students to have like experience like international experience. Like we have also connection with like South Korea, like Singapore and Japan universities. Okay, and we also have like alumni in many like sectors in like both like financial, like in tech sector, industrial sector, and in academic sectors. Okay, so if you want to learn more about our department, you may visit this website, www.math.sc.jula.ac.th. Okay, welcome everyone, and please enjoy the event. Okay, thank you.
Okay, thank you, Associate Professor Achipat Chamlong Chanalak, for the information about the Department of Mathematics and Computer Science, Chulalongkorn University. Okay, so now we are going to start our webinar. So as we begin, I would like to provide a few guidelines to ensure a smooth and productive webinar experience. We have two discussion sessions scheduled during the today webinar. The first discussion will take place following the third speaker, and the second will be after the final speaker. We encourage active participation and invite you to submit any questions using the Q&A option throughout the presentation. To help us direct the questions appropriately, please mention the name of the speaker to whom you are addressing your question. Our speaker will address your question during the designated discussion sections. Okay, so now we are get excited to start it, and without further delay, let us begin with our first speaker, Dr. Howie Shen, on the topic of From Methods to Impact, Capacity Building for Practical Geospatial SAE. Okay, let me give a brief introduction to Dr. Howie. Dr. Howie is the coordinator of the Intersecretariat Working Group of Household Survey. Before she joined the current position in September 2019, she led the program on international migration statistics at the United Nations Statistics Division. She has also worked on many different statistical areas, including gender statistics, population censuses, civil registration, and vital statistics. She holds a PhD degree in statistics from the University of Florida. Kindly join me in welcoming Dr. Howie Shen. Howie Shen, you can start your presentation now.
Thank you so much. Thank you, Japan and Pathan colleagues for inviting me to be a panelist for the session. It's really an honor to work. Can you hear me?
Yeah, we can hear you, but we cannot see you. Is it possible to
okay.
Sure.
Just a second. Let me see. Oh, here. Can you see me?
Okay, I can see you now.
Hello. Good to see you again. Let me share my slides. Great honor to be here. Thank you so much for inviting me. I'll be very brief so I can leave more time for my colleagues who are really truly the experts in the field. But it's really a great honor to be here, and also really great honor to collaborate and be partner with many of the colleagues here today. So I work at UNSD, and I'm also the coordinator as the Intersector Working Group of Household Surveys. I call it ISWGHS. So just to give a little bit of background on what it is, it was a entity established in 2015 under the aegis of the UN Statistical Commission, which consists of chief statisticians, basically national statistical offices from all countries, and also from international and regional organizations. And the Intersector Working Group was established to achieve three major objectives. One is to improve the coordination of household surveys, also to advance cross-cutting survey methodology. Our work on the SAE and Geospatial SAE fall under this, and also to enhance communication and advocacy. So our group currently has 11 international agencies and 10 rotating member states. The Secretariat is with the UN Statistics Division. Our group is currently co-chaired by the World Bank and UN Women. So we conduct our work through time-bound task forces. They're usually led by members of the group, but with contribution from everyone that would like to contribute to the work. And this moment, our biggest task is revision of the, I'm not going to say it out loud, but the UN Handbook on Household Surveys, that the last comprehensive publication on that topic was 1984. So now on the smart estimation, it was also a mandate really from the IGSDGs, many of you might know, but there is this 2030 Agenda for Sustainable Development, and that set 17 goals and 169 targets for us to all of countries and everyone to achieve until the end of 2030. And there's one principle is called leaving no one behind, which means that we need to have data for smaller geographic areas, for population that are typically very difficult to capture in household surveys or in other data sources, especially the very difficult, like marginalized, and we don't really see them. So the IEGSDG is a group that was established that came up that actually set the indicator framework for the 2030 Agenda for Sustainable Development. So that group had requested the Intersector Working Group to support the member states on using the smart estimation methods for more disaggregated data for SDG monitoring. Because there have been a lot of new methodologies on different SDG indicators, but data disaggregation remains a real challenge for many countries. So this is why we have worked together on SAE starting, I think, 2020. And before that, during COVID time, the Intersector Working Group also worked together on the paper that's called Positioning Household Surveys for the Next Decade. So in that paper was really written to support countries and say, because everyone is suffering from COVID, for not able to go to the field for household surveys. So what is the future? How do we really support countries to really handle any crisis or challenges like COVID? And the first technical part, the paper set 8 technical priorities. And the first technical priority is about enhancing interoperability and integration of household surveys, which is hugely linked to SAE that we're talking about. So because with the mandates from the IEGSDGs, and we started to work on really various tools for capacity building that includes, there was a wiki platform called SAE for SDG, a toolkit that has put together different methodologies, country practices, and we try to really bring in what's already there in terms of methods, literatures, and handbooks, methods, conferences, all of the relevant materials. At the same time, we've also been talking to countries and SOs and asked them whether they have been using smart estimation for more disaggregated data. And because the method is not new, it has been there for a long time, and surprisingly and not surprisingly, and what we found is most countries could not really do it, and they have experimented with it once or twice, but they were not able to really take it up to support official statistics production. So in this toolkit, or on the website, we've put together, for example, the methods, practical guidance, but we've also documented national example practices. And when countries were able to use SAE, and we ask, what are the steps that takes you to do all this? How many years it take? When the countries that told us they couldn't do it, then we also asked them why. What are the challenges? What made it so difficult for you to take up the methodology? And then we put together a documentation on the challenges and enabling environment to really move SAE from experimentation to production, to official production. So there are a number of challenges. We all know SAE is a complicated modeling methodologies. Right now, everyone will have the capacity. And then there's also really the support from top management. But one of the key things for many countries that low-income, lower middle-income countries that don't have good administrative data. So either there's not the quality is poor or lack of data access. It's really hard for NSO's National Statistical Office to have access to admin data, to use as input data for SAE for scenario estimation. So to keep that in mind, that's why we have the Geospatial SAE. But overall, it has been very challenging for countries. We see Latin American countries are more advanced, are advancing faster, but then other regions are a bit lagging behind in Asia, countries in Asia and Africa. And of course, there's the hesitation of use of model-based estimates versus design-based. How do you really justify? How do you communicate all the methodologies modeling to users and top management to get support from them? So after the release of the toolkit, I think it was 2022. Yeah. And then 2023, with our partners from ECLAC, Statistics Division. ECLAC is the Economic Commission for Latin America and the Caribbean. And with UNFPA, we developed an e-learning course that has 50 videos and then cover all aspects of SAE modeling. And Patha is one of our instructors over there. Thank you, Patha. So the course was online. I think it was online August 2023. Now we have English, French, and Spanish courses. We have a large number of students, but not everyone actually do it and manage to finish all the course materials through. So we offer self-paced and also guided learnings. And we offer sessions in different regions and then with instructor and SAE experts having office hour for 2 hours every week after the students have watched the video. And then they will go through they'll go through the questions together. And right now I see that with Africa and Asia, our instructor has also been connecting with a specific country students from national offices, ask them to get the data ready and provide support on their modeling. And we also support countries to attend the SAE conference. And then there has been regional training workshops carried out by our colleagues from Asia and from Africa. And then Patha has offered quite a few expert clinics to countries when they really need support on certain aspects of the SAE. There has been a lot of challenges in terms of capacity building, and our skills it's really a challenge, and that not all the students are familiar with linear models. And when there are officials from National Statistical Office, they have to find time working outside of their working hours to join the courses and to really learn. And some are really interested, but the course material is considered very intense and very high level. So as I've mentioned earlier, that many of the feedback from our students and from countries is having access to having good input data in addition to household surveys. They often only have the option of a population census, and access to administrative data has been extremely challenging. So that's why that prop does after I've seen David's presentation, one of the SAE conferences, I thought it was really great methodology to use geospatial data. And and for countries that don't have good access to administrative data. So with David from World Bank and Josh and Partha, and also with the support of IEG SDGs, and then there's UN Geospatial integration with statistics. There is a guide, we call the primer, that we've worked together that gives an overview as SAE method. I'm not going to go very detailed because my colleague is going to cover that presentation. So it talks about geospatial data and training data sets and methods and skills and tools that need to apply the methods and then future research and work. A draft primer, it was available March last year, and we're going to put up another revised version, more final, with new examples in a week time. As a background to the upcoming UN Statistical Commission session. Now, as we have the primer, it's really great to show the methodologies and then also to demonstrate the potential of use geospatial information for SAE, and then having in mind that our NSOs, not everyone is super familiar and often unfamiliar with how to get geospatial information, where to get them, how to work with them, how to run the model with geospatial information. So now we are working together with our colleagues from World Bank, ECA, the Economic Commission for Africa, and also, sorry for misspelling, Economic and Social Commission for Asia and the Pacific. We are working together on a step-by-step guidance, really to illustrate how to do it. And hands-on, and going to be available later this year. I think that's it. So if you are interested in learning SAE, taking e-learning courses, and also geospatial SAE, or receiving technical support for your office, provided if you're SAE expert, you are ready to provide expertise in supporting countries, if you'd like to hear from us on what we do from the Intersector Working Group Housing Surveys, or since we have universities here, if you would like to work as an intern for the UN Statistics Division, please email me at chen9@un.org. Thank you so much.
Okay,
I'm gonna
thank you.
put this in the chat also, my email address.
Okay.
Thank you.
Okay, thank you, Howie Shen, for your excellent presentation in capacity building for practical geospatial SAE. And now for the audience, if you have any questions for Howie, please use the Q&A option. And please also be reminded to put the name of the speaker in order to help us to direct the question appropriately. And thank you, Howie. So next, let's move to our second speaker, Dr. David Newhouse, on the topic of the small area estimation with geospatial data using simple approaches. Okay, let me give a brief introduction to Dr. David. Dr. David Newhouse is a senior economist in the World Bank's Development Economics Data Group and an elected fellow of the Institute of Labor Economics and the International Statistical Institute. His work has focused on economic measurement, including integrating survey data with non-traditional data, and analysis related to poverty and jobs in developing countries. He holds a PhD in economics from Cornell University and has published many articles in respected journals on statistics, labor, poverty, health, and education in developing countries. Please extend a warm welcome to Dr. David Newhouse.
Thank you so much, Jirapan. Can you hear me clearly?
Yeah.
Wonderful. Thank you so much for the invitation to present at this webinar. It's truly an honor, and I want to thank all the participants for taking the time to listen. I want to speak about small area estimation with geospatial data using simpler approaches. I believe my colleague Josh later will speak about some of the more complex approaches, though I will touch on them briefly. Just as a little bit of background and motivation, I think we all understand that household surveys are a critical source of data for socioeconomic measurement. They're the source for much of what we know about how the economy is doing, how households are faring. But they typically cover a limited set of enumeration areas, and we're so used to using them, I think sometimes we can forget about the sampling error that they contain. Because of the limited set of enumeration areas and the limited size of these surveys, which results from their expense primarily, estimates, as we know, are often too unreliable to publish for small areas. So the representative areas for which household sample surveys can be published are often the province or the district, and of course, policymakers would like to go lower. And I'd like to argue primarily that I think we can understand our world better at lower cost by augmenting these sample surveys with publicly available geospatial data. Some of the benefits of geospatial data are that it's always on, it's geographically comprehensive, so perhaps I'm overstating a bit when I say there's no selection bias, but certainly compared to other sources of data like cell phones, where you have to worry that maybe not the whole population has access to a cell phone, geospatial data does at least see more or less everyone. Geospatial data is not good at everything, but it is very good at measuring population density, and this in turn is correlated with many, though not all, socioeconomic outcomes that we're typically interested in measuring. Another real positive aspect of geospatial data is it's often freely available, primarily in two forms. You can download or process raw imagery directly, or there are plenty of useful indicators that have already been derived by geographers and other analysts that describe elements of geospatial data. So I'll give some examples of those. WorldPop, based at the University of Southampton, does an excellent job of modeling population structure and population density. They also make some building data available. Then there's a number of climate indicators that are freely available. These include temperature, drought indices, rainfall, and other things. The OpenStreetMap, which is an open source map of essentially the world. It's not perfect, but you can use it to get useful information about things like distance to major roads. The nighttime lights, which is collected by the VEER satellite launched by NASA. There are estimates of net primary production. There's an open source project to look at these counts of cell phone towers everywhere around the world. Again, perhaps subject to error, but this can be useful. One of the very interesting layers that's available on Google Earth Engine is this one produced by Tsinghua University, which has for every pixel the years since it changed from pervious to impervious surface. So there are a number, I didn't mention at the bottom also that there's land cover classifications, which is very predictive of a number of indicators, which just tells you for each pixel how likely it is to be different classifiers like urban, built up area, forest, grassland, these sorts of things, which is also very useful in many applications. So you can see that linking these to survey data can be very powerful. And I can think of 4 potential applications. There may be more. The first one, which I'll talk mostly about here, is small area estimation to get more precise and disaggregated survey estimates. Another potential application is nowcasting, which involves predicting across time. And this addresses the common complaint that the household survey data we get is often old because it takes quite a bit of time to process and release the data. So there is real demand for up-to-date, what's the latest indication that we have of how people are doing. Then a third potential application that I think hasn't necessarily gotten the attention it deserves, but has a lot of potential for the future, is to do data quality assessments of survey data. So it's the same techniques essentially that are used for small area estimation could also be useful, in my view, to see whether survey data is systematically biased for different indicators, perhaps because the survey did not interview enumeration areas that are perfectly representative of the population. So if the survey data is subject to selection bias, in a sense, this may be something that could be unveiled through linking the survey data with geospatial data. And then a final application is that there's just additional insight that one can obtain from linking disparate data sources. So if you think of household survey data on welfare, for example, and climate data on rainfall, you can think of how households respond to weather shocks. And there's been quite a literature already on that. But one can do it better by linking survey data with satellite data. And there's a lot of other kind of, besides simply looking at households and climate, there's many possible, I'd say, useful things that the geospatial data can say about how households are interacting with their world. So coming back to this first part about smaller estimation, there is this long tradition which was partly developed or popularized, I should say, at the World Bank. It extends a couple decades even before that, of using SAE with census data. But the issue we face, especially in developing countries, is that recent data may not be available, or it's difficult to obtain, or perhaps it doesn't exist. And as Hao Yi said earlier, this raises the prospect that geospatial may be a partial substitute for this, that geospatial data can be used in lieu of census data when the census data is old. And so sort of one question I'll pose is, why not do this routinely? The geospatial data is more or less free, or at least good geospatial data is free. The survey data more and more can be geolocated, certainly at least at the EA level. That's quite common. And so why not do this as long as the benefits in terms of reduced sample error outweigh model error? And because there is error from any model, but it's important to remember that all these samples also have sample error, and incorporating auxiliary data that's geographically comprehensive can help reduce that sample error. So I guess I would argue, as long as we can improve on the direct survey estimates we get from survey data, why not do this integration? Now, I'll talk a little bit about nowcasting, which was the second application that I mentioned. And unfortunately, prediction across time is much more difficult than prediction across space using geospatial data. And I think this is largely because economic changes are not completely visible from the sky, or at least not obviously visible from the sky. You can think of a country entering recession and the buildings don't change particularly. Now, partly, however, this may be just because we don't yet have the right geospatial indicators. And two areas where I think there's room for improvement is, first of all, being able to identify building changes and the pace and nature of new construction. There is some publicly available data available on buildings, but it tends to be from one moment in time, spanning, say, 3 to 5 years. So we don't have the kind of high frequency information on changes in buildings, which could be really useful for this. And then a second area where I'm slightly disappointed with the sort of availability of geospatial data is looking at agricultural crops and yields. And my suspicion is that this is quite hard. There is no, to my knowledge, publicly available, easy to obtain information on agricultural crops and yields. If there were, we might be able to say something, especially in rural areas, about high frequency changes. Having said that, we do have access to existing imagery, and it's quite possible that this is better able to predict economic changes over a longer term period than a shorter term period. So these are some preliminary results from a working paper that should be coming out in a few weeks, done jointly with a team at Stanford University led by David Lobel and Marshall Burke. And the question here that we're looking at is, how well can imagery predict changes in asset index? We're using relatively low resolution imagery here, Landsat, because this is going back to 2007, 2008. And the idea was to link these images to 2 census rounds and just see, using some quite sophisticated deep learning methods, how well we do at explaining changes in a wealth index over a period of 10 years. We looked at this in Malawi and Mozambique, and we could explain about 50% of the changes in the wealth index in Malawi, but only about 30% of the changes in the wealth index in Mozambique. And this is the best case when you're training on all images in the sample. So usually we can't really train a model using all images from around the country. So we'd see worse performance in a more realistic case, and using very complex methods. Kind of transformer models. So, this is all to say that nowcasting is not easy. So I'm going to focus more on smaller estimation in terms of cross-sectional prediction, which is much easier. And so here, I think there are 2 key questions. The first is, how well does geospatial smaller estimation work? Because it doesn't always work. And in particular, as I mentioned, how much does it improve on direct survey estimates? And how would we know? What does this depend on? And then a second question is, how would you go about doing this? What are the pros and cons of different models and methods? Like any statistical exercise, there's lots of different available models and methods. And as part of this is what tools are currently available and what tools will soon be available to make this easier, because we're working on a couple tools, which I'll talk about at the end. So here, the argument I would make, based on a lot of work that we've done, both in these 4 countries, but also in other countries, is that when looking at poverty, which is one of the main applications of small area estimation, and using what I'd call a simple features-based approach, we usually improve on survey estimates. And what this reflects in large part is that there's a strong relationship between household welfare and population density. If you look at where the majority of the extreme poor live, it's in rural areas, like over 80%. And that reflects this strong relationship between household welfare and population density. And this, in turn, the sort of the strong predictive power of geospatial data when predicting population density, and then to a lesser extent poverty estimation, can give us some large increase in the precision of estimates when doing geospatial estimation. So the bars on the left show the correlation with census-based estimates. These are cases where we've been able to validate or evaluate the methods against census data that's been geolocated, which is really, I think, a necessary step for evaluating kind of how well we're doing here. And so what this is saying, for example, is in Burkina Faso, the average correlation at the target area, which I believe was the commune area, was 0.84 for the survey estimates. And when we added the geospatial data, it increased to 0.87. And that may not seem like a lot, but it actually produces quite a bit of increase in the precision of the estimates, even for what may appear like a relatively small increase in correlation. And we do see bigger increases in correlation in other places. This, again, sort of depends on the nature of the sample, depends on the predictive power of geospatial indicators in that particular context. It does vary, but we do generally, for poverty, see that geospatial small area estimation improves on direct estimates. In some cases, the increase in precision can be quite large, on the order of 3 to 7 times. And so because of this, and kind of when you get lucky in a sense and have a good case, you can report more disaggregated estimates with the same level of precision. And these are a couple maps that were featured in the 2021 World Development Report on Data produced by the bank, of an exercise we did in geospatial SAE in Tanzania. The map on the left shows the lowest level of reporting that's feasible with the survey data. And the map on the right shows what we could do when we combine the survey data with the satellite imagery. And what's striking about this is not only that the panel on the right is much more disaggregated, much more informative, and tells kind of a different story about where the pockets of poverty is, but in results that I don't show here, but do in the paper, that the estimates on the right are essentially equally as precise as the estimates on the left. And that increased disaggregation for the same level of precision comes because, in effect, we're adding data to the mix on places where the sample survey did not go. So how much is this improvement? We know it can work in sort of good case scenarios. And how much does it work? Well, it sort of depends on the reduction in sampling error that you get from the auxiliary data versus the introduction of model error that you get from putting estimates, essentially, or using a model. All models are wrong, but some are useful. And so whether this is useful or not depends a lot on how much you're reducing the sampling error and how much model error we're introducing. The model error, in turn, depends on the predictive power of the geospatial data. The geospatial data is not predicted. We won't have a good model, and we may get estimates that are worse than the direct survey estimates. But also another factor is the level at which you're linking the survey with the geospatial data. And in our experience, the geospatial data is much more powerful when you're linking it at a relatively local level, such as a village or a small 1 kilometer square grid or something like this. And there are a couple of ways one can link geospatial data with the survey data. Either you can be fortunate enough to have a village ID in the survey data with a corresponding shapefile that tells you the polygons for each of these villages. This was the case for us in Tanzania. Or you have latitude and longitude of the enumeration areas, and one can construct grids. This is the case we found ourselves in with Burkina Faso and a number of other West African countries in a paper recently published in the Journal of Official Statistics with Nico Savitis, Timo Schmidt, and others. When it works, I'd argue, as I mentioned before, geospatial small area estimation can be valuable. For poverty estimates, we've sort of seen across these 4 countries that we can increase the precision of small area estimates by a factor of 3 to 7 relative to just using the survey data. It depends on the context and the exact indicator and measure of poverty. Again, this sort of reflects the systematic correlation between poverty and population density, which I think is generally true almost everywhere. The way I read this is there's potential for millions of dollars of benefits at negligible cost, because sample surveys cost, can cost upward of $1 million to field. And if we're increasing the precision by factors of 3 to 7, there's a lot of potential value there. I want to talk a little bit about methods and which methods can be used. I can kind of divide the methods into 3 buckets. The first are linear mixed models. I think we naturally gravitated towards this initially because there's such a long tradition dating back to Batiste, Harder, and Fuller in 1988, which actually used satellite imagery and demonstrated proof of concept of combining survey data with satellite imagery like 40 years ago. So linear mixed models have some nice properties. They're design consistent in the sense that as your sample size increases, you get estimates that converge to the true values. And then we do have this body of literature now that we see improvement on direct estimates in many cases. I would argue that if you're trying to do very granular estimation, say at the village level, linear mixed models are probably not the way to go. They do have a fairly restrictive functional form, and we haven't published these results, but in times when we've tried them, they have not performed particularly well for doing, say, village level or grid level prediction. My suspicion here is that, yes, the linear models have some error, but if you're aggregating those to a higher level, like districts or subdistricts, that those errors largely cancel out, at least to some extent, and that makes them effective for sort of more highly aggregated estimates. Now, one can do tree-based machine learning as well. A popular tree-based machine learning is called extreme gradient boosting, or XGBoost. With features. When I say with features, I mean like the table that I put up earlier, like nighttime lights and land classification and those sorts of things that you can download off the internet. And so there's some evidence that the performance is similar to linear mixed models and work I've done with Josh Murfeld for more aggregate estimates. For the more aggregate estimates, whether you do XGBoost or linear mixed models probably doesn't matter a ton, assuming the sample data, the training data is similar to what we see in real life. Also, what's nice about tree-based machine learning is predictions can be reasonably accurate. I have a paper with Melanie Guelavisi in the World Bank Economic Review that show this in Malawi. And then that paper with the Stanford team, which is forthcoming soon, also looked at extreme gradient boosting, and we find reasonable accuracy at highly disaggregated levels. And that's also quite feasible. It's not terribly difficult to do XGBoost. What is difficult are these deep learning models. Maybe some people can do it, but I can't myself, to be honest. And it's not straightforward. And part of the reason for this is that they rely pretty heavily on raw imagery. Then you have to condition that on the geospatial features to get better results. These do give more accurate estimates at a highly granular level. They are difficult and quite resource intensive. So we do need to work on sort of the capacity building side of things and making this more accessible. Just to give some example of these, this is from the paper, the Zheng et al. Paper that's forthcoming soon. We tried transformer models, CNN models, and extreme gradient boosting models. Don't worry for now about the difference between the green and the red. And you can see that the transformer models do the best. They condition on these geo features, so you get the kind of the best of both worlds of using raw imagery and well-defined features. But the difference is not huge. So one can still do the CNNs, one can even do XGBoost in some situations like Malawi. There are also some gains to using transformer models in some settings. And this does seem to be the future, with LLMs kind of slowly taking over the world. So in terms of the linear mixed models, I just want to come back to this, like how would actually one go about doing this? So one option has been dubbed the unit context model. This is kind of a variant of the unit level models that Batiste, Harder, and Fuller developed and were subsequently refined by Molina and Rao. The variance, and the reason it's a little different, is it's only using aggregate levels. And here R is like a regional level, like a province where the survey data is representative. A is the target area, and S is like a sub area, like a grid or a village below the target area level. And we're using the sub area aggregates and their means in the model. But there's actually, because it's geospatial data, we can't link it directly at the level of households in most cases. And so you have to use some aggregate measure. And so we just put it in the model. And other than that, it's just a straightforward linear mix model, which, there's a lot of math here, so it may not be entirely straightforward, but it is well known, and there's a lot of software and sort of material online that explains how linear mix models work. The second approach that one could use is what we call a sub-area model, where we model a transformation of the sub-area level outcome. So, for example, if we're looking at poverty, P bar on the left-hand side would be the poverty rate, and you model that as a function of sub-area and area and covariates and regional dummies, again with a random effect to also take advantage of the survey data effectively as a prior. And so these approaches have some different pros and cons. With unit context models, one of the issues is that it's important to properly adjust for the weights when estimating variance components. This is not at all straightforward, but it is an option in some of the software that we have developed. And then these models do impose a constant variance for all areas. Partha and Nicola Salvati have developed a new method for relaxing this, which is encouraging, which we hope to implement in software very soon. But this can be an issue that the variance is assumed to be constant for all areas. Now, on the other hand, the sub-area models discard information on your continuous welfare if there is a welfare measure doing poverty, and they may be less flexible in a way where there is an underlying variable in the poverty or in the stunting case because they don't model the underlying variable. What we found in a number of evaluations is that both of these work well and neither dominates the other. So in terms of the selection between these two methods for linear mixed models, I do not have strong feelings. It sort of depends on the context and so on, and they both work quite well. What we have found, and what I do believe, is that both of these methods tend to outperform area level models in cases where they've been tested. And I have nothing against area level models. I think they're great. They work well in many cases, and they are really probably the preferred option when auxiliary data is only available at the target area level. However, with geospatial data, you can almost always get auxiliary data at a very low level, like a grid or a village, which may very well be below the target area level. And in these cases, area level models don't do as well because they aggregate this data, and that discards important variation. Often it doesn't make a huge difference, but occasionally it can. And the cases where we've seen where it matters quite a bit is when the sample size is small or the sample is subject to selection bias. And if you think about it, the intuition here is that the lower level auxiliary data can correct for the selection bias when the selection bias is across PSU in some sense. But if you aggregate everything up to the area level, you lose quite a bit of variation, and you lose the ability to correct for some selection bias within the area. There you can see quite a big advantages. And we saw this in Burkina Faso, actually, where we saw when evaluating against unit level models that the unit context model did quite a bit better than the area level models. Okay. A quick question is how to know whether this works. So, I mentioned that it often works if the geospatial data is predictive, but the geospatial data might not always be predictive. And so what we found in other ongoing work is that a useful measure of predictive power for SAE is what we call the marginal area R-squared. And this is essentially the correlation between the average of the dependent variable at the area level and the predicted values of the model, the average of those at the area level. And I would argue that these better reflect the accuracy or the predictive power of the variables, because in the end, we're aggregating everything to the target area anyway. So the goal here is to explain a variation across the target areas. And for that, we want an R-squared that can do that takes that into account. So even if you're missing some of the variation within areas, I would argue that's of second order importance compared to the variation across areas. One way to think about this is if you knew the answer at different areas, like if you somehow magically knew the answer of what poverty was and you put at the area level and you put that in the model, your model would do very well. Better probably than any model without the true answer, even if that other model had unit household level variables. I think the point here is that in terms of diagnosing how well a model is doing, it's useful to look at the variation across target areas more perhaps than the variation within target areas, which is not really something we're after as long as we're explaining the variation across target areas. Why do I say this? Well, in other ongoing work, we've sort of looked at a bunch with Josh and others. We've looked at 19 different human capital outcomes in 4 low and middle income countries, because a lot of the literature so far is focused on poverty. And we're thinking, well, how does this do for human capital indicators? Something like labor force participation or basic water, or whether fertility or whether educational attainment. Can these same techniques sort of save us a lot of money when we're measuring those? And what we found here is when we first removed about 400 cases where the marginal area R squared was less than 0.05. So the geospatial data was not very predictive at all in those cases. This is things like fertility, where it's quite noisy and it's difficult to predict with geospatial data, and it doesn't work well. After we did that, there were only 14 of the approximately remaining 1,500 cases, only 4 of those where the SAE estimates were worse than the direct estimates. And this was maybe bad luck with the sample, or who knows what it was, but we more or less were able to eliminate the cases where the small area estimates were worse than the survey estimates by applying this filter on the marginal area R squared. This is not a scientific rule of thumb. I'm not claiming that. But I am claiming that if you have very low marginal area R squared, something less than 0.05 in a small area estimation model, that is a real warning sign that your model is likely to fail. It means the auxiliary data is not doing the prediction that you need it to do. And so I think it is a useful indicator. Okay, I'll talk briefly about some of the tools that we're developing. We hope to get these out soon. We're still kind of finalizing things and fixing bugs and so on, but maybe in a few months. The first one where I'm very excited about this is called GeoLink. It's designed to be a one-stop shop to link publicly available geospatial features to survey data. So it will essentially, in R, download the geospatial data for you, process it, turn it into what's called zonal statistics, and then merge it with your survey data. It can link either through the latitude and longitude coordinates used supply, or through administrative identifiers with a shapefile. So far, we have a number of indicators with nighttime lights and land classification and model population estimates and OpenStreetMap points of interest, these sorts of things. And I think this will help sort of facilitate the use of geospatial data in survey analysis, just by making it easier for someone like me, who's not really an expert in geospatial data manipulation, to access these indicators. We do have a development version available on GitHub. We're aiming for release in a couple months. The other thing I want to talk about is the POBMAP R package. It builds very closely on something called EMDI, which is an R package that was developed by Timo Schmidt, Nico Savitis, and colleagues, and is currently available on CRAN. Version 1.0 of POBMAP is also available on CRAN. It adds a few features to the EMDI package. We do have a version, a 2.0, with a number of distinguished co-authors in production that adds a ton of features. And so I'm very excited about that. But we have to wait a few months to kind of get things ready. But hopefully the first half of this year, that can get out. It also has to get reviewed. But I think there are some advantages of POBMAP and EMDI. They're quite well documented. They're user-friendly. They can implement sample and population weights in multiple ways, which can be important in some cases. They can estimate unit level and area level models with some recent innovations. There's a wide variety of transformations, including adaptive transformations, which is really neat, where it picks the right parameters for you. It automates and facilitates basic diagnostics. It can parallelize to be fast. It's all fully open source. And version 2.0 is going to implement a number of fantastic new methodologies. So just to tie this up and conclude a bit, I see great potential for integrating survey data with geospatial data for empirical measurements in a variety of fields. I personally feel it can create value worth millions of dollars for indicators that we care about. The main constraints I see right now are kind of lack of tools, lack of knowledge, and lack of awareness that this is useful. And perhaps I could add to that lack of trust. Some national statistics offices don't fully trust model-based estimates. Even now, though others do. So we have some work to do there as well. I think both relatively simple and sophisticated methods can work well. It depends on the context. Simple methods tend to work well for more aggregate estimates. I think in the best case scenario, it is feasible to think that you can generate estimates at one administrative level below the one that the survey is representative at with similar precision by adding the geospatial data. The sophisticated methods are better for highly disaggregated microestimates. They do require more training data, which can be an issue. I think an interesting area for future research is how to boost their performance on small samples. And we are busy trying to develop resources to help, specifically the GeoLink and PodMap R packages, and also as how you mentioned, the primer and the how-to guide on geospatial estimation. That's it for now. I want to thank everybody for listening once more, and I'm happy to take questions after the third speaker. Thank you.
Okay, thank you very much, David, for your engaging presentation on geospatial data and the resources to use geospatial data. So now for the audience, and again, if you have any question, we encourage you to use Q&A option, and our speaker will answer in discussion section. So now let's move to our third speaker, Dr. Joshua Murphy, on the topic of machine learning for SAE. Josh is an associate professor at KDI School of Public Policy and Management in Sejong City, South Korea, a research affiliate at Institute of Labor Economics in Bonn, Germany, and invited researcher with the J-PAL, an affiliated researcher at Global Action for Policy. His research and teaching interests include development, applied microeconomics, agricultural poverty, and environment. He is particularly interested in using new data sources and new empirical methods to improve our understanding of a wide range of outcomes, particularly the SDGs. Please join me in welcoming Dr. Josh Murphy. Okay, Josh, you can start your presentation.
Thanks, Japan, for inviting me. Can everybody hear me and see my screens okay?
Yeah, we can hear you, Kelly.
Great. So like I said, thanks for inviting me. I'm going to continue talking a little bit about geospatial data for small area estimation, but I'm going to change the focus here a bit from what David was talking about. And I'm going to focus more on machine learning. In particular, I'm going to be focusing on machine learning with satellite imagery. David already mentioned a couple times things like XGBoost, gradient boosted trees more generally. And I will get back to that in a bit. But for now, I want to start by kind of just giving an overview of a specific method that's been the most common in satellite imagery and this kind of poverty mapping work, which is convolutional neural networks. At the end, I'll kind of talk about one new method that David also mentioned, which is vision transformers. But for now, what I'd like to do is kind of just provide, like I said, an overview, relatively simple overview of satellite imagery, how we use it in convolutional neural networks, and how these CNNs can allow us to do poverty mapping. So I am going to use, as an example, the country of Malawi. Malawi right here, as you can see, it's in sub-Saharan Africa. It has a very long lake on its eastern side that covers more than half the length of the country. And, you know, when we think about this imagery here, the big question is, how do we take this imagery and then use it in such a way that we can predict something like poverty at relatively smaller, you know, less or more disaggregated areas, right? And the first step here, what we do is we usually break up the country into grid cells, right? So here is Malawi broken up into grid cells, right? You can see the shape mostly matches the actual country itself. But with the difference here being that each one of these is a grid cell, and it might look something like this, right? Now, this grid cell, these grids, they're going to cover the entire country, and by name, right? The grid, each cell is going to have the exact same dimension. Now, the size of those dimensions completely depends on the use case. David talked about an example where each grid cell was essentially 4.5 kilometers by 4.5 kilometers. We're working on another where each grid cell has a resolution of less than 1 kilometer, right? So, the size of the grid cell can change. But what we're going to do is we're going to take this grid cell, these grids, we're going to overlap it with the imagery here, and we're going to extract the image for every single one of these grid cells, right? And we can look at 3 examples. Hopefully you can see this, right? There's 3 little red squares here, right? And let's go through these one by one. So here is the first image from this red grid cell, kind of in the middle of Malawi, but a little bit north of the true middle. Now, as you're looking at this grid cell, you probably in your head have some idea of what kind of environment the people in this grid cell are living in, right? You can see there are some scattered buildings. Those are those brighter white things in the image. You can see that there are some roads, not too many. It seems like there might be some farms around there, maybe some agricultural, some plots, right? But they're also not super green, right? So here's the first image. So here's the second image. You see it's a little bit further north. It still seems like it's mostly rural, but at the same time here you can see that there's this small town, kind of the upper left side of the image, right? That there's some center of, of population in the area, right? And now when you think to yourself, okay, I see this image and I see this image, which one do you think would be more likely to have poverty, higher levels of poverty, right? I think most of us would probably agree that this image, it probably has higher levels of poverty than this image, right? And you can pick out patterns in here that might clue you in to the level of poverty in this grid cell. And then we can go look at one more. And this one is located in the Lilongwe generally metro area, let's call it, right? You can see that this seems to be much more built up, a lot of buildings, right? Some green area, a lot of small roads, things like that. And if I were to ask you to rank this one in terms of welfare relative to these two, I think probably most of us would agree that this one probably has the highest level of, let's call it, human development, something like that, the lowest levels of poverty, right? And we can all, as we look through these different images, pick out the features within these images that kind of clue us into how much poverty there might be in the image, right? And the entire idea behind deep learning with this kind of satellite imagery is to try to train models that can distinguish some of those features across these different individual grid cells, okay? Now, some of those features might be things that we, with our own eyes, also pick out, but they also might be able to pick out much more nuanced features that we completely miss. Things like subtle differences in colors, things like that, right? So these things can actually do very well identifying some of these things within the image that predict poverty. As David said, kind of geospatial data in general is really good at distinguishing places with high levels of population from areas of low level population, right? And one reason that's so much easier to do than some other things is you can just see here clearly because of the number of buildings, there's going to be way more people living here than here. And there's probably likely to be more people living here than here. And it's easy to see in imagery with our own eyes. So models pick it out quite easily as well. And that in and of itself tends to be highly predictive of things like poverty. Okay, so now that we have our images kind of broken up across the entire country, right? We're going to build a model with these images. And what we're going to do is we're going to try to use this model to predict welfare into every single one of those grid cells, right? So this is just an example that if we took every single one of those grid cells that I showed you earlier, and we predict the poverty rate into it, it looks something like this for the entire country of Malawi. All right. So like I said, we're going to train a model. We talked about the imagery. We're going to then predict these poverty rates throughout the entire country. And in this example, these grids are only about 250 meters by 250 meters. So this is a very fine-grained poverty map. Now, whether that's accurate or not is a separate question that's kind of beyond the scope of what I'm going to talk about. But you can see that with this idea, you can get into very disaggregated levels of prediction. So like I said, CNNs, convolutional neural networks, have kind of been the most common tool in this stuff in the last decade or so. It's a form of supervised machine learning. And what that essentially means is that we need to give it labeled data. So in other words, for every single one of those grid cells, I shouldn't say for every single one of those grid cells. For some subset of grid cells, we need to know the amount of poverty in that grid cell, right? The question is, how do we do this? Well, the most common way we do this nowadays is with a household survey, because household surveys very commonly actually have GPS coordinates in them. So for each household, or at least each primary sampling unit, some small, like a village, we have a latitude and longitude that we can actually observe in the data itself. Now, something important about this latitude longitude is that it's usually what we call jittered. What that means is we don't want to allow people to identify the exact location that was surveyed for privacy reasons. So instead, what happens is in the publicly available data, the GPS coordinates will be randomly offset by a couple kilometers, up to a couple kilometers, I should say, right? So you don't know exactly where that household's located, but you know it's somewhere relatively close to where that point is, right? And so if we go back to our grid, right, these are all the households from one household survey that was done in Malawi in 2019, the IHS-5, right? And you can see the location of all the different households. In the very middle, you can see this white rectangle. That is the area I showed you earlier. And if we look in that white rectangle, we can see we have two groups of households, and we can locate those households in a specific grid cell. So if we look up here at that first row of grid cells and the third column, there's households there. It's not one household, it's actually about 16, because that is an entire cluster that was sampled. So we have 16 households there. And what we can do is with those 16 households, we can calculate the mean poverty rate, right? So if, for example, half of them are poor, the poverty rate would be 0.5. And then that grid cell that those households fall within would get labeled as 0.5 poverty. And then if we go down here to the other example, which is also the third column, but here the fifth row, right? Maybe, for example, here only 25% of households are poor. So this cell gets labeled as 0.25. And if we do that for all of the cells that contain households that were surveyed, right, we can get thousands, well, sometimes thousands, but at least hundreds of grid cells with a label attached to them. And then we're going to use that to build the model. Now, one thing to mention is that it's very common to combine methods. And I'm going to come back to this in a second, right? What we're going to do with these CNNs is we're going to predict some outcome we care about. But something that's really nice about these CNNs is that we can actually extract something before that final prediction, before that actual poverty prediction. There's one layer before it that we can actually use. And we can use those in actually a different method. For example, gradient boosted regression trees, which is the example from Chi et al., who put together HDI estimates across the globe. Okay, let me skip this. Now, CNNs, to put them simply, look something like this. And this comes from Towards Data Science, which actually has some really nice explainers for a bunch of different data science methods. So if we look over here on the left, the input, this input is going to be a single grid cell in our example, okay? So we take a single grid cell, right? We're going to do convolutions, and these convolutions are where, of course, the name for CNNs comes from. Exactly what they're doing is not super important here, since we're just kind of looking at a broad explanation. But these convolutions are done over a set of pixels. For example, it could be 3 by 3, so 9 pixels at a time, 4 by 4, 5 by 5, whatever, right? You can change that up. You can change this architecture and fine tune it to make it perform better. And then the last bit, so we take this image and we do all of these convolutions and some other sorts of functions to them. And then what we're going to do is we're going to run it through a neural network. Okay. A neural network is a fancy way to say a bunch of logistic regression, basically, right? Now, to do this, what we have to do is we have to turn our data, this image data that went through all these convolutions, pooling layers, stuff like that, and we have to turn it into a vector. And it turns out when you turn it into a vector, you can actually also append other data to it. So I say, we often combine methods. You can also combine data. You can take satellite imagery, do all these convolutions, and then before you feed it through this last step, this neural network, you can add other things to it as well. For example, you could add other sorts of geospatial data. You could add other kinds of administrative data, stuff like that. And then what we're going to do is we're going to feed this through these neural networks, right? Now, these neural networks are essentially, you could imagine in one layer, you have 10 what are called neurons. And then the next layer, you have 10. And then the next layer, you have 10. And these all fully connect to one another across layers. And then the final layer is going to be the actual prediction step, all right? Now here, this example is doing classification. The example we've been talking about with, for example, poverty is not a classification task. It is a prediction task. So here with classification, you can see this very last layer over on the far right. Each output has a different label. Is this a car? Is this a truck? Is this a van, et cetera, right? With predictions for poverty, this very last layer is not going to have a bunch of different options. It's just going to have one. It's going to be the predicted poverty rate for that image, right? Which in our case is a grid cell. Now, something that's really interesting about this is right before this last layer, you have, when I say this last layer, I mean the actual prediction layer. Right before that prediction, in the penultimate layer, you have usually a bunch of neurons. I use 10 as an example, but it's usually way more than that, right? You could have hundreds or even thousands of neurons in this penultimate layer. And every single one of those is going to have a value associated with it for any given image. So what you can also do is you can extract those values with that very penultimate layer, right? We'll just call them features for now, CNN features. We can extract those and then turn around and use those in a different method like XGBoost. Now, the way the CNN is set up is what we refer to as its architecture, right? CNN architecture is completely flexible. And that's one of the things that actually makes it very difficult to build one yourself, because some of these are incredibly complex. So starting from scratch is often very hard. So what's very common is actually to use what we call a pre-trained model. ResNet, AlexNet, there's a bunch of different ones, right? And this is already pre-trained on some set of images. And what we can then do is we can take that pre-trained model and we can change it slightly. It's called fine tuning. We can change it slightly to make it work better in our specific example, in our context, because the way we're using it is not going to be the same as the way it was originally tuned. So how can we actually use this for small area estimation? Well, I already mentioned earlier, and I showed you a figure that you can just use the pure predictions from the CNN itself, right? You can use that final output, right? That's what I showed you earlier with that map in Malawi. Now, if you just use it straight up out of a CNN, one big problem is that you don't get any variance estimates, right? Now, in data science, in ML and deep learning, this is often not thought of as an issue, but when it comes to national statistics offices and policymakers, they're often, for understandable reasons, somewhat hesitant to use estimates that do not have any sort of variance estimate along with it. So that's where the second option kind of comes in. And this is something I've been working with David and others on recently. And it's to use that penultimate layer, what I was talking about here, this penultimate layer where you could have hundreds or even thousands of neurons. You can take those out and you can essentially simply use those as candidate predictors in a traditional small area estimation model. Alternatively, you could use the final prediction as an input into a traditional small area estimation method. And one of the nice things about these two options is that these methods that David was talking about, they will calculate measures of uncertainty. So, like I said, so here's an example of a pre-trained network called LeNet. And I've cut off the first few layers just to focus on the end. And this is designed to estimate, to classify one of 10 different classes, right? So that means this very last layer, it has 10 because it can be one of 10 different classes. And the layer before it has 84 neurons, right? What we'll call 84 features. We can just extract those 84 values for any given image and use those in an SAE model. Or we could, if this were just, for example, a prediction, just pure prediction, poverty, we could just use that prediction from this very last layer. So an example of the first option is from Ratledge et al. And what they're going to do is they actually use CNNs to predict wealths to then turn around and actually estimate some treatment effects of electricity access, right? So what they do is they simply, well, I shouldn't say simply, right? It's complicated. They estimate a CNN in 2006 and then 2016. This is Uganda. And then they're going to predict wealth into every single one of the grid cells. And you can see those two here, right? A second example is a paper I have with David and others. Is we are going to use the actual predictions from CNNs in a traditional SAE model. So we use CNNs to predict poverty and to predict things like land classification. And then we're going to take those predictions and use them as candidate predictors in a just traditional small area estimation model. And it seems to perform quite well, right? This is an example from that paper of land classification. The far left, you see the actual planet image, right? In the middle, it's the class likelihood for roads. And you can see, right, that it does a very good job of identifying where roads are. And the one on the right is for buildings, same thing. It seems to do a pretty good job of figuring out where buildings are. And then the final example that I want to talk about is a work in progress, where we're trying to use vision transformers instead of CNNs. Vision transformers are relatively new. This name transformer is the key breakthrough that allowed large language models like ChatGPT to get so good in the last 5 years. So these vision transformers share some of these features in common with these large language models. And the big one is this attention mechanism that they use that I'm not going to go into. And we do have some evidence that these vision transformers may perform better than CNNs. David also showed some earlier. And in this paper, like I said, this is still ongoing. Our goal is actually to use features from that penultimate layer in a traditional SAE model instead of just doing a pure prediction into space. This is an example from a paper from 2021 where they were predicting HDI, Human Development Index, but the key thing here is what they have done. This is called mosaics. They have made those features that we've been talking about available for anyone to access. So we have actually been using those features, right, already in some of our work. David mentioned a work on human capital. Well, it turns out some of the features we're using there are these mosaic features. And these features do come from CNNs, right? And they seem to be quite predictive, right? When we use lasso to select different kinds of features to avoid overfitting, these mosaic features are almost always selected, at least some of them, much more so than even some of the more traditional geospatial features. But all of this is still kind of a work in progress. It'll be interesting to see where it goes in the next couple of years. Okay, I'll stop there to make sure we still have plenty of time for questions. Thanks so much for listening.
Yeah. Okay, thank you, Josh, for your presentation on machine learning for small area estimation. And now we are open our Q&A session. So please feel free to submit any questions you have using the Q&A option, and our speaker will address them shortly. Please don't forget to mention the name of the speaker to whom you are addressing your question in order to help us direct the questions to the appropriately to the speaker. So now let me start with the first speaker, Dr. Howie Shen. So this one question is it could become an option to develop a specific gap path, especially for field enumeration, so that the enumerator can easily use a gap path and directly coded the data to send to the server and continue the next statistical process.
Yes, so I just typed something over there. So basically most of the countries in the world have developed or started to use CAPI, computer assisted personal interview. So the enumerator will go with a pre-programmed tablet that started a collection, but that doesn't mean that the interviewer enumerator, they actually still need to fully understand what the survey about, the questions, and to interact with the respondents. So the interviewers still need to be very well trained. But then the CAPI already will have a lot of checking behind it. So if some response is not reasonable, it will pop up to verify, validate. And sometimes also it has its automatic flow skip patterns it can go. So it's all programmed, which is great. When there are countries that have no issue with internet data transfer and then the data are transferred to the supervisors or data center for checking, sometimes countries do have the opportunity to go back to the respondents, and if at the validation stage there are some issues with the survey data.
Okay, thank you for your answer. Okay, I think we have only one question for Howie. Okay, so let's move to the second speaker, Dr. David.
Okay, so we have a question from Harold about the estimation of populations using remote sensing data. So I think one thought I would give on that is it's going to be a lot easier probably to use predefined features like land classification or building polygons if they can be obtained, and they probably can be for this type of population modeling. I'm very optimistic that geospatial data can do this quite well. But I'm not sure you need to go into the investment of kind of accurately identifying and classifying roofing materials from satellite imagery yourself. If you can do that, that would be great, but that is not easy. It requires training a CNN or vision transformer model, downloading the raw imagery, et cetera, et cetera, et cetera. It's much easier to download pre-existing indicators that already exist on places like Google Earth Engine or elsewhere. And then let's see. I think Harold also asked about what methods I would recommend for correlating with these population estimates. I guess it depends on the level of disaggregation that you're looking for. If you're looking for highly disaggregated estimates, I might try some tree-based machine learning models like extreme gradient boosting. If they're relatively aggregate, maybe linear mixed models wouldn't be so bad. But it depends on the context. And so I can't answer with 100% confidence without knowing the details. From Daniel, I think, asked about the R-squared in Malawi and Mozambique and why the R-squared was higher in Malawi. I think this might partly be the level of disaggregation of the data. In Malawi, we were able to get census data disaggregated to the enumeration area level, which is perhaps smaller than the level that we were able to get at Mozambique. So that could be part of it. It could also have to do with the structure of the country in terms of where wealth is located. It's possible, for example, that a higher proportion of wealth in Malawi is located in urban areas, which the satellite data therefore might better be able to predict that in Malawi. We don't know exactly, so it's a good question and perhaps worth looking into further. But I think the main point I was trying to make is that nothing necessarily works well in every context. The predictive performance varies from context to context. Santanu asked about subarea models, and I do claim that subarea models are preferred to area level models, at least for these types of analyses. How can you use subarea level models when subarea indicator is not available in the survey data? I think here you do need the survey data to do this kind of data integration. So we can only predict something that would be a measurable in a survey. Or in its data source that can be linked to the geospatial data. And so that, yes, that linking has to happen. Once you have subarea level estimates, how can you aggregate it? I think the easy answer is use POBMAP or EMDI, which kind of does the aggregation for you. It will estimate a model at the subarea level that includes the variance components. It will add simulate the variance components by drawing from their estimated distributions, and do that repeatedly and aggregate it up to the higher level. So it sort of makes it easy for people to do this kind of aggregation to a higher level. I think that may be it for me. Are there any that I missed?
Yeah, I think that's all. I can see questions for you also. Thank you very much. Okay, so now we move to the third speaker, Josh.
Okay, sorry, let me get my video.
So glad you have a few.
All right, yes, so on the first question, I don't think I would say that geospatial data can only be used for things like poverty, but I would say that it seems to be easier to predict than some other things.
Sorry, Josh.
Oh, sorry.
Yeah.
The question was that it seems using geospatial data to improve survey data will be more reliable for poverty indicators because it would be based on things like buildings and structures, whereas health indicators could differ and be impossible to estimate was the question. And I don't think I'd say impossible to estimate. I think I would say harder to estimate. I think it's important to keep in mind that when we talk about using geospatial data, we're not suggesting that you can only use geospatial data. If you have, for example, access to administrative data, so some countries, including in low and middle income countries, have lists of, for example, the location of health centers, hospitals, things like that. You could use those. I guess that would technically be geospatial data, but it's also administrative data. So I could imagine that there are predictors that would help us with human capital, but it does seem that, at least for now, the more common geospatial predictors do better with poverty than they do with some of these other things we care about. The second question is about matching grids to shape files. The short answer, Fifi, is that we create the grid ourselves. So you have a shape file for Malawi, right? You see the outline of the country. You get imagery that covers a little bit more than just the country. And what you do is you create a grid yourself of whatever size you want. And then you just keep those individual grid cells that overlap with the country. And then you take those grid cells to basically, you can imagine taking scissors to the image. That's basically what we do with the grid cells. We overlay a grid cell and then we cut out the image for that square. Third question. To use this is quite a complex estimation technique. Is it based on connected volumes or what? I don't see you giving examples of precision estimates using CNN and SAE, sampling errors, hard squared, stuff like that. Yeah, so in this presentation, I did not do that. Of course, if you have, for example, a census, you could try some new CNN and see how well it correlates with truth. You could do something like cross-validation to check. I did not show those. My goal here was just kind of go and have an overview of what the methods are about. But you could calculate those. The one thing CNNs are harder to, one thing that's a little bit harder about CNNs though, is that you cannot calculate variance estimates, at least not in a straightforward way. Whereas these traditional SAE methods that David talked about, you can. And let's see, there's another one now. What could be the use case of geospatial data for SAE other than poverty estimate? So like I said, this is still something we're kind of exploring, to be honest. We started with poverty. We're working now on human capital, different kinds of human capital. Some, it seems to do a pretty good job, others less so. I think some of that is because certain things, so for example, educational attainment is highly correlated with welfare, with poverty. So if you can predict poverty well, you can probably predict educational attainment pretty well. But yeah, the short answer is we're still kind of working on that.
Okay, thank you, Josh, for answering the question. I can see one question for general speaker. Let me read out the question and any of you can answer. The first question, I am a PhD candidate at the University of Northern Colorado, and I'm searching on topics like developing development learning methods in SAE for my final research. Or any possible internship? Is there any chance to introduce sources, ongoing projects, and potential state of the art of topics that I can try or work on them? Then any speaker have an answer to this question? Or you have suggestion on the topic?
So Jerapad, I guess I might say that sort of thing that's probably best discussed bilaterally. So if the person wants to email me or anyone else, they're welcome to. And because it's probably too detailed to get into in great depth here.
Okay, then we suggest to wait for the second discussion session. Then Dr. Pahili will answer this question, right? Okay, another question. Thanks for the interesting and relevant presentation. Question for the first and second speakers. How do we make these techniques or methodologies accessible to governments in developing countries who might not have all the technical capacities to replicate them?
Should I come in? And then my colleagues to come in. They've have tons of experience building capacities. So I see this as we have the small area estimation wiki platform. We have the e-learning course, so it's open to everyone. It's free. Everyone can just sign up and then join the course. It's hosted by UNSD. But it needs also a lot of countries usually to make it work requires a lot of hands-on training, work with real data sets. So our course does have real or synthetic data that you can work with. So if your office is interested in more in-depth training, so use all the materials that are included in my presentation. But if your office, NSO, or government organizations interested in more in-depth support, with experts going there really to work with the technical person or all the colleagues over there, please reach out to me and then we'll see whether we can have funding to support more in-depth, because it's the training, the e-learning course is just the first step, right? And then work with your own data, cleaning the data, get the data ready for the model. So it's a whole package. We'd be happy to support it, but just reach out to us. It requires a lot more. Yes.
Okay, David, do you have any comment on this one?
Just a quick comment that I think the packages are very important here for capacity building, and which is why we're putting quite a bit of time into them. And the documentation of the packages really taught me a lot about SAE, and I'm hoping that the GeoLink and PubMap packages will also help spread the word and help build capacity.
Okay, we have a few minutes, and we have a few questions not directly to any specific speaker. Let me read out the question, and any of you can jump in. So the first question: why do we directly estimate our poverty rather than focusing on intermediate characteristics strongly correlated with poverty?
Can I jump in here, actually? So I think, first of all, I didn't mean to give the impression that geospatial data could only be useful for smaller estimation of poverty. I think, as Josh mentioned, it can be useful for a number of other outcomes, though we are still exploring which outcomes work well and which outcomes might work less well. A second point is that poverty is kind of first order importance because it often informs the targeting of social assistance programs. And so that's one key application. Another application is it's often useful to evaluate the impact of spatial projects or programs or policies on poverty outcomes. Though, one could envision that this could be useful for other outcomes besides poverty as well. It is kind of an especially important outcome.
One more question. For small island geographics, grid site need to be able to consider data confidentiality. So what can be the determinants or determining site grid?
So I'll say something just because I think I'm the one who talked about grids. Or I should say I think I'm the only one who talked about grids. The size of the grid is often it's often more based on the kind of data that you have available to you. So what I mean by that is that certain kinds of geospatial data, the resolution is quite low. And when I say the resolution, what I mean is that how much that data varies across space. So some kinds of data, the resolution is very low, so you only see like 1 kilometer by 1 kilometer. It all has the same value. And then you go over to the next cell and everything has the same value, 1 kilometer by 1 kilometer. So there are some data sets that are 5 kilometers, the resolution. So if you have a 5-kilometer resolution for your data, it wouldn't make any sense, at least if that were your main source of data, it wouldn't make any sense to have grid cells that were smaller than that. So the grid cells aren't really about data confidentiality per se. The data confidentiality usually comes into how the survey data is processed and the kind of data that is released to the public. So the NSO that does, like Malawian NSO, they do an excellent job. They have the household survey coordinates and they know where the households are located, but they are going to, before they release the data, jitter those coordinates to protect the confidentiality, the privacy of the respondents themselves. So that's not the data confidentiality is not really about the grid cell per se.
Okay, thank you a lot. So from my record, I think we have addressed all the questions, and now it's time to start our second part of the webinar. Then let me introduce the next speaker, Professor Pata Lahili, on the topic of can geospatial auxiliary variables be beneficial in small area estimation? If so, how can they be effectively utilized? Okay, let me give a brief introduction to Professor Pata Lahili. So he is a professor in the JOY program in survey methodology and the Department of Mathematics at the University of Maryland College Park. He currently serves as a director of the JOY program in survey methodology. His research interests encompass data linkage, Bayesian statistics, survey sampling, and small area estimation. He has actively contributed to the field by serving on the editorial boards of many international journals and many advisory committees. He holds a fellowship in the American Statistical Association, the Institute of the Mathematical Statistics, and is an elected member of the International Statistical Institute. In recognition of his outstanding contribution to the research, application, and education in small area estimation, Dr. Lahili received the 2020 SAE Award. And he is now serving as the president-elect of the International Association of Survey Statisticians. Please join me in welcoming Professor Pata Lahili.
Okay, good. Okay, so my talk would be like this. Can geospatial auxiliary variable be beneficial in small area estimation? If so, how can they be effectively utilized? Well, I am going to present something that I have been doing with my collaborator and students. Specifically, I would like to mention the contribution from my recent collaborator, Priyanka Anjay, a student, current PhD student, Yuding Chen, former student, Shantanu Pramanik, my collaborator from Italy, Nicola Salvati, and Jirapan over here. Okay, as David mentioned that this geospatial data in small area estimation is actually not new. There is a paper by Bettis, Harter, and Fuller that he mentioned. I will also give some idea about what they did in that paper, and then I'll present certain new things. At the beginning, I would like to clarify that in small area estimation, there are spatial models on the outcome variable, and that is not what we are talking about here. What we are talking about here, the availability of auxiliary information that is very useful in small area estimation are available so that the location can be identified, either by means of longitude, latitude, or some other way. So that's what we are talking about. So let me give you one example from agriculture where one may interview farmers to get different kinds of information like acreage under corn or soybean or rice. But some information can be also available from satellite. For example, number of pixel classified as corn or soybean or rice. The question is, can we use the survey data along with the satellite information to produce estimate at granular level, say at the district level or even below that? So this is the paper by Betty Sutter Fuller. I just presented a table from their paper. Basically, they were interested in estimating acreage under corn and soybean for the counties which are below the state in the state of Iowa, specifically north central Iowa. They were considering 12 counties there, and they have some information from the farmer. Specifically, they know how much corn or soybean there for different segment, which is roughly 1 square mile in their sampled in the sample that they have directly from the farmer. Now, they also have information from satellite, but the good thing is that the satellite information is available not only for the sampled segment, but for all the segments in the county. And this could correlate well with the problem in mind, and hence there is a possibility of improving estimation. So here is the graph that I take from their paper. On the x-axis, you have the information coming from the satellites, specifically number of pixel classified as corn for different countries, and we have 12 different countries. And the y-axis is the information that we are getting from the farmer. So as you can see, the information that we get from the farmer is highly correlated with the information we are getting from the satellite. And so the idea would be how to produce estimates of corn for different counties. And that was done by them using a linear mixed model that David also talked about. My next example is a very recent work I have been doing with my Indian collaborator, Priyanka Anjay and Santanu Pramanik. I mentioned their name earlier. So here we are trying to understand whether there is any correlation between some outcome variable. Specifically, we looked at the population size and the poverty rate, okay, with nighttime light data, which can be treated as geospatial data, because you can get this information at a very granular level. So hopefully this might be very useful. First of all, I would like to make a comment that we believe that if these geospatial data can be used at a very granular level, just like the paper of Betty Sutter Fuller, we feel that could be very useful. And using this Indian data, we found that evidence. First of all, we did it at the state level for various states where you have, for example, population size or the poverty rate, and we also have average nighttime light density. And we didn't find a lot of correlation when you did the analysis for the state level. But then we looked at the district level for a sample of states, and we found quite interesting result. For example, the table that you see is basically the correlation between population size that you get from 2011 census, that's the last census India had, and the nighttime light data. It's the mean intensity of nighttime light. And these states, if you look at it, first of all, let's focus on aggregate. What we mean by that, we looked at the population count for each of the district in the states. And then we try to see what's the correlation with the nighttime light data. And you get a positive correlation throughout. But we think it is much more useful if we kind of break the data into urban area and rural area. And if you look at the correlation of the population size with the nighttime light data, for the urban area, first of all, it's positive and correlation is quite high. On the other hand, for rural areas, it's negatively. They're also quite high, except for a few states like Orissa and West Bengal. And we have some reason why we are not getting high correlation there. Okay, so now let's look at the next table. Here we are looking at poverty rate for 2022. Of course, we had to do some work here. First of all, the poverty line was not available for 2022. It was available only for 2011. So we used the inflation factor to get the poverty line. And then we had a survey of 2022, 2023, where we get the consumer expenditure data. And then we use the poverty rate estimation from there and try to see what kind of correlation we get. Now, we see that for both urban and rural area, the correlation is negative, which makes a lot of sense. And they are quite high. Now, for some of the states, it's not great, especially for rural area. And one reason might be, we still need to investigate this, but one reason might be that one of the variables, they are kind of flat over the various districts. Now let us focus on one particular state, and we choose the West Bengal. And we are looking at the relationship between population size and mean brightness, that is the nighttime data. And we are looking at for the districts. Now, one thing we see that the correlation coefficient is 0.50, but the graph is very strange. There is an unusual observation on mean brightness, and that is the biggest city in West Bengal, Kolkata. So if we eliminate that Kolkata from the data, then we see the correlation coefficient increases to 0.75 and the graph looks much nicer. So what it points us probably that when modeling the small area, we may have to consider different kinds of model for different kinds of different groups of small area, indicating some heterogeneity in the data across area that we are considering, in this case, the district. Now, let me move to some work that I have done with my colleague in Italy, Nicola Salvati, and this appeared in GRSSB last year. And this is also related to geospatial data in the sense the auxiliary variable, that is the elevation that we consider, are available at different location, and longitude and latitude information is there. So this comes under geospatial data as well. So basically, it is a problem of Environmental Protection Agency studying the health of US lakes in the northeast part of the United States. There are like roughly 21,000 lakes in the northeastern part of the United States that we are considering here. And 334 lakes were selected by some sampling mechanism. And then this small area here is what is known as hydrogeologic unit codes, which is a certain groups of lakes, And it turns out that 27 HUCs are out of the sample, and many of them have very small samples, like a very small number of lakes there. And the outcome variable of interest here is the acid neutralization capacity, or ANC, for the small area that we are considering. So let's try to understand the data set. So this graph that you see here, on the y-axis, you have ANC, that is the outcome variable of interest here. On the x-axis, you have the HUC, which are the small areas, and we simply looking at the box plot of the data. And you can see there are a lot of heterogeneity in data, both within area and also across area. Then we like to use some model. So at the beginning, what we looked at, we are trying to understand whether the intercept of a regression model, if you run for different areas, which is the HUC code, are similar or not. So we see a lot of variability of the intercept estimate across different small areas. And we also see some variation of the slope, which is the elevation. Elevation is the auxiliary variable that we are considering that is available there. So now let's try to introduce the model. We need a little bit of notation. We have M small areas. Here the small areas are HUC code of the lakes. And capital Ni is the population size. That would be like number of lakes within the HUC for each area. And Y is the outcome variable. X is the set of auxiliary variable. In this case, we are considering elevation here. So we have one auxiliary variable. And I is the index for the small area, which is the HUC code. And J is the unit, which is the lake in this example. So we are interested in the parameter, which is the population mean, which is basically, if you get the ANC value, the outcome variable value for each and every unit, that is the lake in a HUC, you average them out, that is the population mean or the average ANC, but that's unknown because that's referring to the unknown population here. So we have a sample, I mentioned that we have a sample of only 336 lakes out of some 21,000 lakes in that region. So Ni is the sample, that is the number of lakes that we have for the ith small area, that is the HUC, and it's not large enough. And I already mentioned many of them have like 5 or less number of lakes in area, and about 27 of them, they don't have any data there. And so if you want to use a direct estimate, which is sample mean for the area under consideration, and that would be very unreliable because of the small sample that we have. And for some of them, we cannot even use the data because there is no information coming from the survey. So we consider a model, this nested regression model. Let me first give the model that Bettis-Harter-Fuller use. It's the usual unit level model that we talk about in small area estimation. So there is a fixed part, which is the beta naught plus xij prime beta. X again is the auxiliary variable that's available at the unit level. And then there is a random effect from the area, which is gamma I, and then the usual error that's there in every model. And we assume that the random effects are normally distributed with mean 0 and variance sigma gamma square. And we have also assumed normal distribution for the epsilon, that is the model error. So the model parameters sigma square gamma and sigma square epsilon are referred to as variance component. So this is the well-known Bettis-Harter-Fuller model that they use to estimate acreage under corn and soybean in the paper that I mentioned before. Now, what we noticed in our work is that there are variability, there are heterogeneity in the model parameter. For example, the sigma squared, epsilon squared, they actually vary across area, and so are the slope parameter. So we kind of extended the model. We call it extension of the nested regression model that Bettis-Harter-Fuller used. So the difference with the Betty-Sutter-Fuller model is that we are now allowing regression coefficients beta I to vary across area, in this case, a HUC code. And we are also assuming that the sampling variances are also varying, that is sigma square epsilon r varying, because we notice it from the preliminary data analysis. So we have a new model, and then the problem of interest is estimation of average ANC for different HUC code. And then basically we used the best predictor of the population of interest, which is the average UNC code. And I have some formula written here, and more details are obtained from the paper that I mentioned, that is Lahiri Salvati 2024 GRSSB paper. But I just wanted to say that this is a weighted average of direct estimator and the synthetic estimator. So it would be interesting to see the maps showing the spatial variation in the HUC, which is area specific elevation slope coefficient left, and the sampling variance. And we concluded from this kind of preliminary analysis that it is not very reasonable to assume the regression coefficient remain the same for all the areas, small areas we are considering, and same is true for the sampling variance. So the extension of the nested error model makes a lot of sense. We have a lot of other preliminary analysis done, and we concluded that's the right model to use. And then we produce estimates of the maps using the direct method that is coming directly from the sample survey information, and also the empirical best predictor, which combines information from the survey data and the auxiliary variable, in this case, the elevation, And we saw a lot of difference in the maps. For example, if you go this area, this is dark, much darker than this area. And if we look at the map more carefully, notice a lot of difference. And we also have produced tables, and it showed they're clearly different because the information that we used are different. For EBP, we use more information. Now, it would be on interest to look at the box plot showing the ratio between the coefficient of variations of the direct estimate, which is the quality measure for the direct, and the coefficient of variation of the estimates obtained by the model that we used, that is with the heterogeneous nested regression model. So values greater than 1 indicate the CVs of the direct estimates are higher than the other ones. So if we look at this box plot here, which plots the CV, that we can see based on this criteria that empirical best prediction method that used this extension of nested error model is doing very well. Now, this R package is available in Nicola's website. So in case you want to use this method, you can go to this GitHub page and download the code and apply it to your situation. Thank you very much for listening. I would like to mention one thing is that when we study the correlation of the outcome variable and the auxiliary variable, for example, in the Indian example, for the population count, there is no issue because the data coming from the census. But a lot of times you have to do it based on the survey data, which has a lot of sampling variability. And so the question is, how do you study the correlation? Because if you include some very, very small area, that might distort the relationship. Okay, so what we've done in our case, we consider those areas which are relatively medium-sized sample size. But if you want to include all the areas in the correlation analysis, I would recommend a paper that I wrote with Jirafan here in Shonka 2015, and that can give you a better idea about how to study the correlation. The other thing that I would like to say here, a lot of times we study how small area estimation doing, in this case using geospatial data to estimate the mean. But a lot of times it is of interest for some other problem like ranking the small area based on some outcome variables, or what are the areas that are above or below certain threshold, or variety of things. And one question would be, if you use the right kind of method there, how useful the geospatial variable. But that would be a research topic for the future. Thank you very much.
Okay, thank you very much, Professor Liley, for your inspiring presentation on the use of geospatial auxiliary variable in small area estimation. And if any of you have questions for Professor Liley, please use Q&A question and he will answer you at the discussion section. Okay, so now we are moved to our last speaker, Mr. Abhesh Kamor, on the topic of lesson learned, use of geospatial information for small area estimation in Sri Lanka. Okay, let me give a brief introduction to him. Abhesh serves as the head of the Research, Assessment, and Monitoring RAM unit at the United Nations World Food Programme in Sri Lanka. With over 10 years of experiences at World Food Programme, he has worked in Tajikistan, Sudan, and Nepal. He's specializing in food security monitoring, vulnerability analysis, digital transformation, and government capacity strengthened. He holds a master's degree in computer science with a specialization in data science from the University of Illinois. Please give a warm welcome to Mr. Abhesh.
Thank you, Jirafan. Just wanted to check if you can hear me.
Yeah, we can hear you.
Great, thank you. So hello, everyone. First of all, thank you for having me as one of the panelists. It's an honor and a pleasure to represent the World Food Programme in this forum. Like Jirafan mentioned, now that our eminent speakers have taught a lot of details on small area estimation and the use of geospatial information on improving the estimates, I would like to shift a little bit of attention from the theory and the technical bits to its applicability, with a specific focus on the World Food Programme. And I'm sure you would all agree that after all the technical presentations, your brain cells also need a little bit of a rest. So yeah, I'm here to do that. So let me start with a bit of a shameless promotion of my agency where I work. It's the World Food Programme. It's the world's largest humanitarian agency. It plays a very big role in providing countries around the world with estimates on food security using various different methods, some of which I'll go through now. WFP conducts very large-scale household surveys through face-to-face interviews, through mobile phone-based surveys to collect and analyze real-time data on food security, nutrition, and also markets, and also analyzing how food security changes with seasons. We have a big GIS-based teams in the organization. So we routinely conduct remote sensing analysis to monitor climate shocks, health, crop health, and different environmental factors that affect food security. So as a result of all those endeavors on data collection, analysis, and reporting, we come up with regular products very frequently. So they include household food security reports, emergency assessments, market monitors, seasonal monitors. We engage in a lot of food security related research. We also have we routinely conduct joint assessments with our partners, UN agencies and other agencies. And we also do a lot of climate analysis, such as the integrated context analysis. So you can see that I'm really happy to share that WFP is a heavily data-driven agency. It's one of our main goals to make decisions based on field evidence. Shifting the focus on the household food security, measuring food security at the household level. So we have, over the past couple of decades, developed indicators that allow us to measure food insecurity. I'll just go through a few of them, key ones. One is called the food consumption score, which is essentially a composite indicator of dietary diversity, frequency, and nutritional quality of household food consumption. We also try to understand the level of coping strategies the household engage in to ensure the food is on their table. We also do a lot of expenditure analysis. And one of the indicators we use is the total the expense of food on the total expenditure, which helps us understand the economic vulnerability and food access for the households. Small area estimation in WFP is, to be honest, is not a new thing. We have, I was involved in one as far back as 2015. So yes, you can see that a lot of discussions on small area estimation focuses on measuring poverty. But we do have reports published through from various country offices, in this particular instance, Nepal and Cambodia, to measure poverty, malnutrition, but also food insecurity. These reports have typically relied on traditional methods in which you use a census survey and a nationally representative household survey to derive estimates, administrative records, and some level of GIS analysis. So now narrowing our focus, because I work in WFP Sri Lanka, so I would like to highlight a few things in terms of how we thought small area estimates would help make better decisions and provide more insight into food insecurity at a granular level in Sri Lanka. So we had a few, let's say, research questions or a few issues that we thought SAE would help us address. Obviously, everybody wants data at a lower level. We are no exception. The granularity of the estimates, reliable estimates, the better our decision making. So our surveys typically provide information on at district level. There are 25 districts in Sri Lanka. But yes, obviously, if you have identified a district, a few districts for intervention, then you would like to know further about the districts, right? And that's where the survey data, given that their representativeness and at district level, give you problems when you want to make decisions within the districts. We also would like to support a few government-led initiatives. There is one called the District Food Security Network. It's a local sub-district level food security monitoring mechanism that they have. And also, WFP and WFP Sri Lanka is no exception, spends a lot of its resources on collecting large-scale household survey data. So obviously, we would like to maximize its utilization, and we try to find various ways in which we can do that. So in Sri Lanka, we took, and this is a relatively new thing here. We wanted to see, once we realized, okay, maybe small area estimation is the way to go for to fulfill all the let's say objectives highlighted before. We said, okay, so how do we go about it? So we did a few let's say capacity development activities with the Department of Census and Statistics of the government of Sri Lanka, which and they have been excellent in their level of collaboration and support. I believe one of the main persons is in the audience right now. So big thank you to Madam Dilshani. We also engaged with the University of Maryland and Chulalongkorn University, particularly Dr. Partha and Dr. Jirafan, without which we would not be able to embark on this SAA journey in Sri Lanka. And then in-house and supported by our regional and headquarters, regional offices and the headquarters, we carried out research into, okay, what are the geospatial variables that correlate with food security? And obviously, our previous panelists have also mentioned that there are a lot of open source data sets that are available, and we use them. They do require, if you want to go deeper and if you want to generate more variables based on the raw data sets, you will have to do specific GIS remote sensing analysis. We're lucky to have that kind of expertise within our team. So that helps us, create some of the GIS variables that were maybe not publicly available, but we have relied a lot on publicly available data sets, and if indicators are available, we have used them too. So these are some of the indicators that we used for the small area estimation using the geospatial variables. These have already been mentioned more than once during this presentation, during this webinar. So I will not go deep into it, but yes, information like building footprints, road density, night light intensity, EVIs, enhanced vegetation index. They're very frequent, very commonly used. And also, there are some indicators developed within WFP. They are very standardized. So if Sri Lanka can do it, any other country office, any other where WFP is operational, can generate these things. Like these include flood risk index, landslide risk index, drought risk index. So if you look at the assortment of variables here, you can see that some relate to identifying areas as, let's say, urban-rural divide. The others, agriculture, some are climate risks. So we try to put them together to see what, when you fit them into an SAE model as an auxiliary variables, how they perform. And again, special thanks to Professor Jirafan for helping us do that. I believe we are also going to publish a report based on the research that was done, which will be very useful. These are some of the analysis we did to identify variables that were shown before and how they perform with food insecurity indicators. In this particular instance, the food consumption score. So you can see, it's not mind-blowing, but there is correlation, small to medium. I guess as you build more indicators, as you identify more indicators that are mildly even small level of correlation, you will understand, you will get let's say better estimates at lower level. And these are the more indicators that we found to have some meaningful correlation with food security indicators like flood risk, landslide risks. We have to be careful on this one, not to get too carried away with correlations. So that's where subject matter expertise comes handy, because just because things are correlated doesn't mean, I mean, they are, I mean, there's a causation that one is causing the other. So even in this instance, I have to admit that a lot of the building and infrastructure indicators have a better correlation with poverty than food security. But since food security and poverty are also highly correlated issues, indicators, one can confidently use it for food security measurement as well. But we know the fallacy with correlation. You can even find a correlation between drownings and ice creams, number of ice creams sold. So yeah, a word of advice to be a bit more careful on which indicators you want to include. So so this is what we did. So after fitting the model with the correlation with the variables that we found to be correlated with food security, we ran it to the model, and then this was the output again, thanks to Professor Jirafan. So you can see how we managed to have a disaggregated level of information from 25 districts produced through the household survey with very good degree of reliability, to 332 DS divisions, which are one level below the district level disaggregation. So, and you can see how this map can be useful for people, especially in my area of work, to tell the decision makers in my organization and other and outside where can you focus within a district. And this is especially useful for organization like WFP, which relies, whose let's say main mandate is to find the most vulnerable people and areas across the globe. So this gives us a very good, entry point into these areas for intervention. So I would just conclude with a few remarks. Overall, through this exercise, we have found that, yes, using geospatial carefully vetted and chosen geospatial auxiliary variable, they show promise in generating food security related estimates at levels where your survey data cannot. And, to be honest, it really should not. It's just too expensive, too extensive. It's probably not worth investing. But we also recognize the importance, and which has been mentioned again, to pick the features that are suitable for your let's say thematic analysis. In our case, food insecurity. So subject matter expertise is very important. And let's say an amalgamation of subject matter expertise and technical know-how on a small area estimation is almost the perfect combination for taking this approach forward in an organization. Widespread availability of GIS datasets. We have talked. There are lots and lots of datasets available. It's just a matter of being able to find them and use them for your purpose. And speaking about WFP in general, we do see, I personally do see there's a great potential to mainstream SAE techniques into our regular food security analysis activity. I believe David also mentioned, to make this activity a regular part of any analysis. Small area estimation traditionally is thought of being a once in a decade kind of activity where you wait for census data, you wait for large scale household survey typically carried out by statistical agencies, and then you start doing it. Given that we have so much data, even within WFP, I can right now tell you somebody is doing a household survey at this point somewhere in the world. So there's so much data within our organization that we definitely should look into it as a valid, robust technique for lower level estimation. We do kind of such analysis in our own way. But I think small area estimation techniques give you a very robust and elegant framework. My real exposure to a small area estimation has been since we got this project going. And having, being a student of data science, I can really appreciate the beauty and elegance of some of the area level model in our case, where you try to see wherever the minimum variance, and you take that part of the estimate. It's a very cool technique, let's say, in my personal experience. And the final word is I think it's really important for verification of these results. Clearly, they rely on it's a model-based technique, and one of our panelists have already highlighted that there's a bit of reticence on using model-based technique, especially when you're producing national statistics. So field level verification, I would say, is you just take a sample of some areas and you verify through some field research. Yes, this is all from my side. And again, thank you for listening, and have a good day.
Okay, thank you, Abesh, for your presentation on geospatial information in Sri Lanka. So if you have any question for Abesh, please use Q&A question, and he will answer the question shortly. So now we open the second Q&A section. Please feel free to submit any questions to the two speakers you have using the Q&A option, and they will answer your question shortly. So let's begin with the first speaker, Dr. Lahili.
So I see some questions. Let's see. Okay, a couple of questions around nighttime light. And the first question is about what kind of sources they use for nighttime light. Frankly speaking, I do not know that much of details. Maybe one of my collaborators can answer this question. So I'll get back to you later on that. The second question is on nightlife. It says the comparison of correlation between rural and urban state in terms of nightlife intensity, is it not obvious because of level of development, industrialization, or electrification? Yeah, it is quite intuitive, but we wanted to see whether it comes out clearly in the database that we have. Because first of all, we have to understand if they are correlated, and how can we make this auxiliary data better. For example, there could be lots of different options. We can consider not categorizing it like urban rural and consider the aggregate, and we found out it is much better to go into the details. The granular that you get on this is better. Now, the second question I see is on some model assumption that we made. And the question is, let's see, about the assumption that we make on the random effects. And the question is, in your specification of random effects, why was the structural random effect not included? I noticed you used only the unstructured random effect. I do not know if I understand the question clearly, but there could be a variety of assumptions that you can make on the random effects. But one thing I would like to say here, if you assume random effects also vary across area, and also the sampling variances, there might be some estimation issue, but if you have some auxiliary variable, that can explain the random effect, you can certainly include that in the modeling. And I think at the beginning, some student asked a question from University of Colorado, about the research topic. I think it is too specific. You are encouraged to contact me if you like, and we can discuss offline.
Okay. Thank you, Dr. Lahili. So next, let's move to Abesh.
Thank you, Jirafan. I see one for me. So
Yeah.
if you talk using census data in SA, some countries do not, due to various reasons, are not able to conduct census. What are the alternatives? FS indicators are critical. Yes, Daniel. So I believe the presentation you saw from our side and the analysis done did not use census data. It used household surveys, large-scale household surveys carried out by WFP, and it used the geospatial indicator as auxiliary variables into the small area estimation model. So yes, at the very least, you would need these two pieces of information to build a model that could help you get food security indicators at some level. Obviously, you would need to work on understanding which indicators fit best for you, plus a thorough analysis of the errors. The coefficient of variation is one of the tools that are used to estimate. So to understand how are these estimates reliable enough. So yes, one of the objectives of having this webinar is what if you don't have a census data? And in case of Sri Lanka, we did not. Our census data is 2012. That was when the last census was done, and that's one of the reasons why we started looking at the geospatial variables to carry out food security estimates at a lower level. I hope that answers that question. Thank you.
Okay, I see another question for you.
Okay, thank you. WFP survey data is at high administrative level. Province, in this case, can we verify SA results that are produced at far below administrative level? So I would say if you, I think by verifying, you mean maybe generating estimates at a lower level. So in our case, we had district level representation, and we managed to take it down to one level below with fairly high reliability, barring some areas where sample sizes were quite low, household surveys were to begin with. So yes, I would say it can be done if you have good enough sample. All the provinces at the household level are available. You can do a small area estimation at the lower level, provided you have again any auxiliary variable, and for the purpose of this discussion, we are focusing on geospatial variables, right? Yes, so it can be done.
Okay, thank you for your answer. So since our webinar is a hybrid event, let's open the floor for our on-site participants. Do you guys have any questions to any of the speakers? Okay, so it's so glad we don't have any question from on-site participants, and no more questions from the online also. So I think that before we close the discussion session, let me give information on our next webinar. Okay. So as a member of IASS Executive Committee, I'm pleased to invite you to join our next webinar, official statistics on population parameters from a non-probability sample or by integration with a probability sample by Professor Danny Pfefferman. The event is going to take place on January 29 at 2 to 3:30 p.m. Central Time. And you can check the information on our website. And we also have the QR code on the screen. It's not showing up on the screen, on the start. Okay, sorry. So this one, at the bottom of the screen, you can see the QR code. On the right-hand side, you can sign up for the webinar. And on the left-hand side, you can check out our website, IASS website, that you can get updated information on upcoming webinar. Okay, before we begin, before we close the webinar, on behalf of the organizers, I would like to extend our sincere thanks to our speakers for their insightful contributions and to the staff for their support in making this event a success. Thanks to all the students, Yuting and Sijita from the University of Maryland and Mr. Virapat from Chulalongkorn University, who assist us with the webinar. And we also appreciate all participants for joining us today. This concludes today's webinar, and we look forward to welcoming you to our future events. Thank you and have a good day. Bye-bye.